Okay. Thanks for returning. I know it's like late in the afternoon. So let's summarize where we are. So towards designing a robust estimator for the mean of a high-dimensional and identity covariance Gaussian, we tried to argue that if the covariance is close to the empirical covariance is what it should be, then the empirical mean works. We are almost done proving that for the case that we have only additive corruptions. In particular, we were at the point that we had established these facts that if the true mean is 0, then the empirical mean of the entire data set is an epsilon fraction of the empirical mean of the added corrupted data and an analogous relation for the empirical covariance. And eventually, via simple calculation, we got what we wanted. So if the spectral norm of sigma hat is small, then the empirical mean works. Okay, so the proof is almost done. The only thing that remains, we were at the setting of assuming that the sample was infinite, and therefore the empirical values for the good data converge to their true values, the empirical mean to mu, which is 0, and the empirical covariance to identity. This is easy, very easy to handle in this case. So you don't need that. So the only thing that you need is that they're going to be close. The mean, the empirical mean of the good data to the true mean in Euclidean norm, and to the empirical covariance of the good data to the true covariance in spectral norm. And these are standard concentration inequalities. So the same proof goes through even with finite sample size, and in particular with this many samples. That's the end of the proof. So a question is like, where do we use that the data is actually Gaussian in this lemma? The answer is we didn't, right? So the only thing we knew, we wrote down some formulas for the empirical mean and the empirical covariance, and we show what we get what we want. So the only thing that we used here is that the empiricals converge relatively fast to the true value. So the only assumption that you need, and of course that you know the covariance with the good data before. Okay, that's the only assumption. Now we're going to move to prove our key lemma. The key lemma again is as if the empirical covariance is close to what it should be, then the empirical mean works. For the strong corruption model, we can have both added and subtracted samples. So this is the version of the lemma. So n epsilon corrupted samples in the strong model, 1 plus delta perturbation in the empirical covariance results in this type of perturbation in the mean. So this is exactly the same as before for the additive case, but this additive term now is epsilon root log as opposed to epsilon. So this is what we're trying to prove. The proof is going to be qualitatively very similar. 75% of the calculations are identical, but we need to handle with the additive power of the adversary to remove some, at most an epsilon fraction of the good data. So, and the adversary can do that arbitrarily. Okay? So this brings us to the second idea that is in this paper. Conceptually, removing any epsilon fraction of the good data, no matter where you remove them from, does not move the empirical mean and covariance by much. Using this additional idea, what we have done so far suffices to establish this lemma. This is very easy to establish in one dimension. Okay, we argued that, but it's true also in high dimensions, and the proof is literally a few lines of calculation. All right, so let's do that. So now the difference is that the set S of corrupted data is going to have the G, the good set, and some subset of size of fraction epsilon from G has been removed by the adversary. Okay, this L we never see. So these are the samples that the adversary removed from the good data, and they could remove them adversarially. The only thing that we know that L is a subset of G, and L is an epsilon fraction of G, or at most an epsilon fraction of G. So we're going to do the exact same calculations as before. So we're going to write the empirical mean and the empirical covariance as the fraction of the sets G, L, and B. Okay, it's brain dead. Okay, so again, we're going to make the assumption that the number of samples goes to infinity. Therefore, the empirical mean of the good data converges to the true value, which for simplicity is 0. So we get the same claim as before, or more or less the same claim, that mu hat, the empirical mean of the good data, is epsilon times the empirical mean of the added data minus epsilon times the empirical mean of the subtracted data. So this is in the previous case of added corruptions, this thing did not exist. Okay, it's just a generalization of the previous claim, or the previous claim 1. So this is what we have so far. And we do the same thing for the empirical covariance, sigma hat. So now it's going to be a little bit more complicated. I'm going to define the empirical covariance of G, okay, the empirical covariance of B, B is the added corrupted data, and this empirical covariance-like matrix for L. These are the data that were removed from G. So note that this is not a covariance matrix because I haven't subtracted the mu hat of L, I have subtracted 0, which so happens to be the mean of the that we're looking for. Okay, so that's just for simplicity. And again, the empirical quantities of G converge to their true values. And the claim is we have a similar, horribly looking formula for sigma hat as a function of B, L, and G, but I have replaced G by the limiting values. So what is that? So there is an identity thing, which is what happens in the limit for G. There is an epsilon fraction of the covariance matrix of B plus epsilon, this rank 1 thing from the empirical mean of B, minus epsilon of this matrix, mu hat L, and then there is epsilon squared times this rank 1 of these differences. Okay, this again a calculation which anyone can do. Now, what happens with these two? So we have established these two things, claim 1 and claim 2. I want to say that we're done here, as before, but we're not exactly. So in particular, what we need to see how bad this mu hat L and this matrix and this vector are going to be. Okay, how large is this vector going to be in L2 distance, and how large this matrix is going to be in spectral norm. If we can bound those things uniformly, then we can do similar calculations as before. And indeed, the third claim, the new claim that we need, which is basically a quantitative version of this second idea, is that the effect that you get from removing an epsilon fraction of the data is not that bad. In particular, the spectral norm of this matrix is bounded by log 1 over epsilon. So the epsilon is because it's an epsilon fraction of the data, of the good data, and the empirical mean is also small, it's at most root log 1 over epsilon. So this is a direct generalization of the fact that if you have a one-dimensional Gaussian and you remove an epsilon fraction of the probability mass, the worst thing you can do is remove it from an epsilon tail, and if you do that, then you mean the mean, which is a number in this case, by this amount, and basically you change the covariance by epsilon log 1 over epsilon. The epsilon is because of the fraction. Okay, so this is the claim. If we have this claim, then with claim 1 and claim 2, we're done. Exactly the same calculation as before. So I can write sigma hat using claim 2, but then whatever I don't understand, in particular I don't understand mu hat L and capital M hat L, I use claim 3. So basically I get a similar formula as before, identity plus epsilon sigma hat B plus epsilon mu hat B transpose, times a matrix that I know is going to have a spectral norm at most epsilon log 1 over epsilon, and this epsilon comes essentially from that term. Okay, and after I have that, then the entire sort of proof goes through. I get that the spectral norm of sigma hat is at least 1, which I get from identity, plus something non-negative because this is PSD, plus epsilon minus epsilon squared times z squared minus this quantity. Okay. And after that, it's just a calculation. We have shown that the spectral norm of the empirical covariance at least this quantity. So if it is at most plus 1 plus delta, then we know that the contribution of the added corrupted points is going to be at most this function, root delta over epsilon plus root log 1 over epsilon. I multiply that by epsilon, I get the answer. So we know that the empirical mean is epsilon mu hat B minus mu hat L, that's like claim 1. So the final error is essentially the length of this vector, which at most by triangle inequality that. We know an upper bound of mu hat B by this inequality. We know an upper bound of mu hat L from this here. So overall, we get the answer. Okay, so the additional idea is the exact same calculation. The additional idea is that removing an epsilon fraction of the data does not have a very big effect, but it does have a measurable effect, in particular more significant than before. This is why we get this additional root log. All right? So nothing more is happening than this conceptual thing. Yes?
So you need Gaussian behavior tails, or did you?
I'm gonna say that now. Okay, so this lemma for claim 3 does need to assume something about something more than what the previous additive lemma was using. In particular, for us to be able to have that the effect of removing an epsilon fraction that has this sort of bounded effect, we need sub-Gaussian concentration. So we don't need the distribution to be Gaussian, but we need every one-dimensional projection to have sub-Gaussian tails. To see that, we just need to see the proof of this claim. So here is a claim. The claim is that this matrix M hat L, which is this empirical thing. So we take all the good samples that you have subtracted, and you take their sort of covariance-like thing. It's useful to actually write that as an expectation over an empirical distribution. So this means that X is a random variable that is drawn from the empirical distribution over the set L. So with probability 1 over side of L, you can get Xi. So this is just useful to rewrite it like that. And we want to prove this claim. And now this claim does need to use something about the good data. So L, the set L, is a subset of the good data. It's a subset of G. So we need to use that. Yes?
Okay, so for mu L at least, sort of you're integrating x times e to the minus x squared, right?
Yeah.
So if it's not e to the minus x squared, if it's e to the minus x, you still get something.
I mean, if you didn't have exactly Gaussian concentration, you had something a little bit worse. These things give you something similar, okay? So let me do the calculation since you're asking. I actually intended to skip that, but I think it's like the one part where this proof is different. So what is this spectral norm? Okay, it's basically by definition the maximum of the expectation of the inner product squareds for any unit vector v. Okay, that's the definition of the spectral norm of this matrix. And now I'm going to use the fact that L is a subset of the good data. So what does this inequality mean here? So I take any event of the probability space, any event calligraphic E. So the left-hand side here is the number of points of L that satisfy this event. Yes? But this probability is just a fraction. So this left-hand side is the number of points of L that satisfy this event. The right-hand side is the number of points of G that satisfy this event. Okay? And L is a subset of G. Therefore, this is a valid inequality. So if you rewrite it a little bit, so we know that L is an epsilon fraction of S. So we get that the probability of any event under L is at most 1 over epsilon times the probability of the same event under G. And G is Gaussian data. Therefore, I know it has light tails. Therefore, I can prove upper bounds on the tail of, let's say, some event using the upper bound of the tail for G. So this is going to be useful to bound this spectral norm. So I want to bound this spectral norm, which is this expectation. This is the expectation of a square. So it's the expectation of a non-negative random variable. I can rewrite it by the integral, the probability that's bigger than something times something. Okay, this is an identity. The first line is an identity. Okay, it's basically the fact that for any z, which is non-negative, the expectation of z is the integral z is bigger than t, probability z is bigger than t dt. Okay? Now, the thing is I need to bound this probability. Okay, this is the tail probability for the set L. I'm going to use the line above. So this is certainly at most 1 over epsilon times the corresponding tail probability for G. But G are the good data. Okay, G have Gaussian concentration. So I know that this probability here is going to be at most e to the minus t squared over 2. Okay, this is what Ravi said. If I had some other concentration here, I can plug it in and get a similar type of bound. So why do I have this minimum of 1, etc.? Because this 1 over epsilon times probability for small values of t is going to be bigger than 1. So certainly I don't want to integrate something that's a probability is bigger than 1 in some regime. So let's calculate this integral. So I know that this quantity here is at most e to the minus t squared over 2. So this suggests that I should break this integral when t is smaller than square root log 1 over epsilon and bigger than square root log 1 over epsilon. So I do that. So for the first regime, where t is between 0 and square root log 1 over epsilon, I just take the 1 in the minimum. So I get the integral t dt. In the second regime, I'm going to get the tail bound of the Gaussian times t dt. So I calculate this integral, and really the first term is the term that dominates, which gives us basically a log 1 over epsilon plus a constant, so log 1 over epsilon. And that's it. So this gives us a bound on the spectral norm of m hat L. And by definition, this vector is upper bounded by that. Okay, because the difference between the two is actually the covariance matrix of L, which is PSD. So this is the proof. I mean, if you don't follow every step, it's okay. Yes?
So L is a subset of the good points, but it gets to pick L after seeing the good points?
That's the thing. So yes. So the point here is that no matter what L is, so the only thing that we used is that L is a subset of G and it has size and epsilon fraction of the size of G. Under those assumptions, this inequality is true and therefore everything else follows.
I see, but the adversary could pick a smaller set than epsilon?
It can, yeah. You're worried about the log 1 over epsilon. So if the size of L is an epsilon prime fraction of the size of G, and epsilon prime is very small, this would be log 1 over epsilon prime, right? So you're saying you're afraid that's going to be very large. But at the end of the day, what I care is this multiplied by the size of L, by the size of L divided by the size of S. So at the end of the day, the worst case is when you actually remove an epsilon fraction for what we care about. Okay? So this is the one calculation that's going to be maybe useful later in one of the algorithms. If you have different type of concentration for the good data, you get different types of bounds. Okay? So this is for sub-Gaussian concentration. So let me move forwards. I think I spent like 13 minutes on this. Okay, so now we have the basic lemma, the key lemma that says if the empirical covariance is what we expect it to be, then the empirical mean works. But we don't have an algorithm. So what do we do? So this, we gave a certificate under which the standard estimator, the estimator we would have used without corruptions, will work. So how do we exploit that? This work by Lai, Rao, and Mepala uses a recursive dimension halving technique. And this is what I'm going to explain. So their idea is that, so this works for additive corruptions, that additive corruptions can actually move the covariance matrix in some of the directions, but not in all of the directions simultaneously. So the noise can hurt you in some directions, but not in all directions. And that's the key idea in what they do. So let me say it once more. You look at the spectrum of the empirical covariance matrix. If there were no corruptions, it would be uniform, it would be spherical. It would be 1 in every direction. The point is that it cannot be much bigger than 1 in every direction. And we're going to show that in at least half of the directions, it's going to be close to 1, and this allows us to reduce the dimension of the problem by half. Okay, so here is a procedure. So we would like to find a large subspace. In this case, it's going to be a linear subspace, where the empirical mean works. Okay, compute the empirical mean in that subspace, and then it recurs on the complement. And at the end, patch the results together. Okay, that's the goal. Of course, the subspace needs to be of large dimension because you can always do that with a one-dimensional projection. But then I would be adding many subproblems. I want to add few subproblems. And the idea is that you can actually do that by reducing the dimension by a factor of 2 in each step. So let me be a little bit more concrete. What is this large subspace? So this is what we're going to call a good subspace. So it's a subspace where the empirical mean works. And note that, okay, now I'm going to use the Gaussian assumption for simplicity. The projection of your data on any, of your good data on any subspace is going to be Gaussian, right? I mean, appropriately rotated, but by what not. But we can actually apply the key lemma there. So if the projection of the empirical covariance on some subspace has no large eigenvalues, then on that subspace I can use the empirical mean. So this is what we essentially showed. And the difficulty is to find such a G, such a bold italic G. So this is not a good set, just a subspace. So how do we do that? I think I gave you the answer. The answer comes from this intuition that the noise cannot hurt you in all directions simultaneously. So the lemma says, and this is now very subtle, it's important, every word is important here. So we get the epsilon corrupted samples, and we do naive pruning. We apply this operation of removing the obvious outliers, the things that are very far out. That's extremely important. After we do that, then sigma hat now is going to be the empirical covariance of the samples that remain. Then the middle eigenvalue of that matrix, you order them, is going to be at most 1 plus of epsilon, which means the bottom half is going to be small. Okay? And we have that if we just use the span of the bottom half of the eigenvalues, then this is going to be a good subspace. All right? That's the idea. Is there anything confusing here? We're going to prove this good subspace lemma. It's very easy to show. Okay, so the algorithm is going to be, before I show you the algorithm, I'm going to show you how to prove this good subspace lemma. Again, this is a quantification of the idea that the noise cannot hurt you simultaneously in all directions, so it cannot hurt the spectrum simultaneously in all directions. So same setup, epsilon corrupted set of samples additively. The mean of the true data is supposed to be 0 for simplicity. The set S is good, union bad. Good is the IID Gaussian ones, bad are the ones that the adversary added. So we're going to do naive pruning. We're going to remove a subset of B by that. So S prime is the set that we get after we do naive pruning on S, removing the obvious outliers. Naive pruning doesn't remove any of the good points, because the good points are on the right distance from the mean. It potentially removes some of the bad points. So the set S prime we're going to have after the naive pruning is going to be G, the good set, union, a subset of the bad set. And the important property we're going to need, that none of the points in this set is going to be too far out. In particular, the distance from the mean of every point is going to be order of root D. The mean is 0, so the Euclidean norm of every vector in S prime is going to be order of root D. Is this clear what we have so far? So we started from the corrupted set. We removed the obvious outliers by using this Gaussian annulus theorem. We remove potentially a subset of the added points. And we know that for all the points that remain, the Euclidean norm is going to be order of root D. So let's look at the spectrum of this matrix. It's a PSD matrix. We're going to look at the eigenvalues. And our goal is to show that the middle eigenvalue, so we order them, the middle eigenvalue is going to be at most 1 plus epsilon. So how are we going to do that? There are two claims. One is that none of the eigenvalues is going to become very small after you add points. In particular, the minimum one is not going to be smaller than 1 minus epsilon. Again, if there were no corrupted points, every eigenvalue would be close to 1. So here I'm saying that no eigenvalue can become smaller than 1 minus epsilon. Lambda 1 is the smallest one. And the next one is the sum of the eigenvalues. It's not going to be much bigger than what it should be. So it should be D. It can increase by at most epsilon times D. So by combining these two claims, we get what we want. So let me show that. So we have these two claims. So let's see. So the first claim says that if you take the bottom half of the eigenvalues, it's going to be at least D over 2 times 1 minus epsilon, because each one of them is going to be at least lambda 1. And of course, the upper half is going to be at most D over 2 times the middle eigenvalue. Okay? And then the second claim, the one about the trace, says that the sum of all the eigenvalues, so A plus B, is going to be at most D times 1 plus epsilon. So we just reorder a little bit, get that B is going to be at most, or B is the sum of the upper part, it's going to be at most D over 2 times 1 plus epsilon, and therefore, because B is lower bound by that, the middle eigenvalue is going to be at most 1 plus epsilon. Okay, that's a proof. Like nothing amazing is happening, but we need to prove claim 1 and claim 2, so it's just definitional. So claim 1, the smallest eigenvalue is at least 1 minus epsilon. So I get S prime, which is the set that I obtain after the naive pruning, and I have a formula that I calculated in the previous lemma, the lemma from the previous lecture, that tells us how the empirical covariance for this set is going to look like. It's going to have a component coming from the identity, a component coming from the covariance matrix of the added corrupted data, and a component coming from this rank 1 matrix of the means. And from that, let's say, take this matrix to be some mu. The minimum eigenvalue of this matrix, at least 1 minus epsilon times the minimum eigenvalue of this mu, okay? It's at least 1 minus epsilon because this matrix is essentially PSD. Okay, that's the first lemma. No eigenvalue can become very small. Now let's try to prove the claim about the trace is a little bit more interesting. So again, sigma hat S prime is the empirical covariance of the data after the naive pruning. We take the eigenspectrum of this matrix, we sum all the eigenvalues. They should be D. The claim is it will be at least D times 1 plus epsilon. And again, I'm going to use the formula for this matrix, for the covariance matrix of S prime. It's exactly the same as before. So what do I do from here? Do you see it? I mean, the trace is linear. So I'm going to get a term which is D times 1 minus epsilon from that, right? And then I'm going to get basically the trace of this matrix, which is sigma B prime hat plus mu transpose. Do we agree with this inequality? That this follows from this. And now the question is, what is going to be this matrix that I need to bound the eigenvalues, the trace of? Well, this is just going to be this sum, because this is the empirical covariance matrix plus what I subtract when I define it. So it's going to be 1 over size of B times the sum over all points of B, xi transpose. So now what happens?
Cycle the trace. Take the trace of this, you get norm squareds.
Yeah. So basically, what do I use? I mean, the claim is that this trace is going to be at most D. Okay, but why? Because every one of those points, every one of those xi's, even though they are corrupted points, they have L2 norm at most root D. This is because of the naive pruning. So each one of those terms is going to have contribution appropriately bounded, and therefore the trace of this matrix is of D, and that's it. So the naive pruning was crucial, and it's crucial to also apply the subspaces, as we're going to see. So that's the algorithm at the end. So we start from the D-dimensional space, from RD. We do the naive pruning there. And then we look at the spectrum of the empirical covariance after the naive pruning. On the bottom half, the smallest eigenvalues, we use the empirical mean, and then we do recursion on the upper half. Note that the recursion is going to go again here, and you need to do outlier removal, you need to do naive pruning on the subspace. So the naive pruning needs to be applied on every recursive step, when the dimension goes down. Okay, and eventually we terminate when the dimension becomes small. Okay, and basically the algorithm is basically a tree where you stop. The algorithm is basically something like that. Okay, this is where the log comes from. You just use, how we're going to have at most log D levels of the recursion, because we start from dimension D, the dimension reduced by a factor of 2 in every iteration. So overall, the error is going to be epsilon root log D. Questions? Yes.
So I see how, so in the first part of the algorithm, you can always remove the bottom eigenvalues are okay, but what makes it okay after removing those first two, right? So is that something you're going to explain, or like?
I mean, I'm done with this algorithm, so if you have any questions, please ask them now.
You worry about conditioning, is that what you're saying?
So, what part of removing the bottom ones makes half of the upper ones better?
This is a lemma that holds in every sort of, in every recursive step. Okay, so if in every recursive step you're going to work with V, the projection of the distribution on V is going to be Gaussian. It's going to be an epsilon corrupted Gaussian. The noise doesn't increase by doing the projection. Therefore, you can apply the exact same lemma on V. So redo spectral decomposition. I mean, you can rotate if you like.
The projection is not quite a Gaussian because you conditioned on
Okay. But you don't need it to be a Gaussian. This is like for the purpose of, I mean, there are some deterministic regularity conditions that you need in the beginning, and with those, the algorithm goes through. Okay, so and in fact, we didn't really need that it is a Gaussian for this subspace lemma. We just needed some basic conditions, right?
Can you just explain what it means to say recurse on V? What information from W did we pass to V and how?
I mean, you know in what subspace you are, so you can retransform, and then you have samples from that subspace, from that distribution.
How did we use the empirical mean on W here?
No, I mean just mean. So basically, if you solve the problem on V, and you solve the problem on W, you can patch these two things together to estimate the mean of the whole thing. That's the only thing that this says.
I see. Okay. So
And the estimator on W is just going to be the empirical mean, so you get rid of half of the dimensions with just doing something that works.
I see. Okay.
And for the rest, you redo. So eventually, you're going. So this step here is going to be, I don't know, median or something like that. Okay. Yes.
So when you go to these smaller subspaces, you're conditioning on having bigger eigenvalues in those directions. So what makes the naive pruning work?
Right. So I mean, this is a sort of technical question. The short answer is that as long as the dimension, so this is like kind of formally wrong, right? So you can stop in dimension log n over epsilon here. And if the dimension is at most that, you can solve the problem by brute force, because 2 to the d is poly. But up to the dimension log n over epsilon and above, the Gaussian concentration works. Okay, so yeah, in very low dimensions, the naive pruning doesn't work, but you don't need to go to very low dimensions. So this is formally wrong. This should say the dimension is at least log 1 over epsilon, then solve the problem by brute force doing Tukey media. Okay, well, that's it for this algorithm. In the next half an hour, I'm going to talk about my work. So this is these two related methods of iterative filtering and soft outlier removal. So let me connect a little bit with what has happened so far. So the way that the recursive dimension halving algorithm works is that it solves a problem many times on lower dimension subspaces and then patches the answer. Now what we're going to do, so it uses some lower dimensional structure of the problem. What we're going to do is we're going to do an iterative outlier removal by looking only at one dimensional subspaces. So this is what these methods do. So the idea is that we want to remove some of the data, not too many, some of the data points, to fix the empirical covariance. So if we're able to find a subset of the data such that the empirical covariance after we remove that subset is close to identity, then by our key lemma, the empirical mean is going to work on that remaining subset. And this is the idea for this algorithm. So fix the empirical covariance, and for the more general versions of this problem, fix the moments, the higher moments. Okay. So step one, we have seen so far the certificate for the empirical estimator working, which is this spectral norm of the covariance being what it should be. And step two is the new thing. So if this certificate is violated, in particular if the spectral norm of sigma hat is large, then we're going to use this information to detect and remove outliers. And we'll do this many times until we're done. Until step one says this subset works. The spectral norm of this particular subset of the data is close to 1. So this works very generally. So for the mean, it remains to, so we have like 30% of the algorithm so far. Okay, so the algorithm is look at your entire data sets, check if the spectral norm of the empirical covariance is larger than 1 plus epsilon log 1 over epsilon. If it is not, output the empirical mean. If it is, what do we know? So what happens if there exists a large direction? Okay, so this is what this algorithm is doing. So what we do is that we project the data in that direction, yes?
Are we doing pruning here?
No, we don't need to. We don't need to. We can. It's going to make the algorithm somewhat faster, but we don't need to. So some of the calculations later suggest that we do, but this is just for, we don't need to do naive pruning here. So the algorithm, the way it is, would actually remove automatically the points that are very far out. Okay, So suppose that there is a large eigenvalue. We look at the direction of maximum variance, or a direction of large variance, okay, larger than this. And the claim is that in this direction, the data would look something like that. There will be a large bump corresponding to the good data, the Gaussian that has this true mean. This is what we're looking for, but we don't know what it is. There's going to be like a significant fraction of the outliers, which are pretty far from the true mean. And the intuition for that is that otherwise, the direction of V star wouldn't have as large variance as we assumed, because this is like an epsilon fraction of the data, and it contributes a lot to the variance. So it has to look something like that. It doesn't need to look exactly like that, but qualitatively this is the picture. So if you projected all the points in the direction, I guess this V star and this V are the same, it would look something like that. I guess all these points should be on the line. So what do you see from this picture? So how would you remove outliers in this picture?
Probably remove the red ones, because they seem to be red.
So the red ones are the corrupted ones, right? And the black ones are the good ones. So what we're going to do, this is good. So what we're going to do, we're going to find some point t on the real line, some threshold, capital T, and appropriately, I haven't said how, and remove everything above it. Okay? And if we do that, our hope is that the red points above that line are going to be significantly more than the black ones. Otherwise, we have a problem. And now suppose we can do that. Why would this even work? I mean, there are many things that are unspecified here. Number one is why such a threshold T exists. Okay, like in this picture it exists, but it's unclear it exists in general. And the second is that even if you're able to do that, you would be removing good points. But if you're able to show that you're removing more red points than good points, then you're in good shape, because of the idea that we explained earlier, that removing a small fraction of good data, no matter when you remove them from, doesn't change the parameters by lots. Okay? The thing is that there is at most an epsilon fraction of red points overall. So if you're removing fewer black points than red points, then you're in good shape because of this fact. Now, one thing that I should say is that for this algorithm, it's pretty crucial that you do that you actually remove good points as well. Okay? And there was a previous paper back in 2009 in a related by different setting, or like robustly learning linear separators, that was using something like that for doing outlier removal in a different setting. The way they were doing it was removing only good data, and because of that they were getting polylogarithmic dependency of the dimension. And in the concurrent work by Santos, Lai, and Rao, there was also an algorithm of that flavor of removing outliers based on the highest variance direction. But again, the issue was similar. Okay, it was not for the mean. I think it was like for estimating the spectral norm, right? So it's pretty crucial that we actually remove black points as well, as long as we can control how many we remove. Okay. Okay. So now let me be a little bit more quantitative about this algorithm. So again, we project all the points on the direction of maximum variance, and we find the threshold T such that this horrible condition is satisfied. Let me read this. It says that the fraction, so this is an empirical fraction, the fraction of points of the set S, S is the set of the entire set that we observe, whose projections in the V direction are far from the median of the projection, is large. Okay? This is this condition I'm going to explain, and after we find such a threshold T, assuming we find it, then we just throw away all the points that are above the threshold. So that's the idea. Now, why does it work? Intuitively, we know that there is a subset of S that are the Gaussian points, roughly speaking, and these have good concentration. So we know that the median is a robust estimator of the mean. So if you take every point of S that's a good point, then the probability of this event is going to be small. And in fact, the constant here is going to be at most 2. Okay, so the good points are not going to satisfy that. It's extreme, like the fraction of good points that are far from their median in this direction is less than a quarter of what we have here. So if we're able to actually find a significant fraction of S that satisfies this inequality, it means that most of the points that we have found are actually red and not blue. That's the argument. Okay? And we can quantify this. Now, of course, there is one important piece missing, and this is that this threshold T that I assume that I can find actually exists. First of all, is it obvious that if this T exists, we can actually find it efficiently? Right, so let's see. So this is an empirical probability. Okay, so the only values that change the left-hand side are basically values v star dot x for x in S. So literally, there's a small number of T's that we need to check. So efficiently, we can check all possible values of T that are relevant and see what the fraction in the left-hand side is, compare it to the right-hand side, and based on that, see if there exists a T with this property or not. So computation is easy. Now let's see why it works. Again, the first claim, which is not entirely obvious, but it is true, is that in each iteration, we actually remove more corrupted than uncorrupted points, more red than black points. And after a number of iterations, we have removed all corrupted points, because there's at most an epsilon fraction, and at most as many uncorrupted points, so we're good. So at the end of the day, the algorithm looks at smaller and smaller subsets of the initial set of points until it finds a subset whose empirical covariance is bounded, and as a result, because of the key lemma, its empirical mean works. And throughout this process, it only removes at most a 2 epsilon fraction of the points overall, because in every iteration it removes fewer red points than bad points, and the total number of red points at most an epsilon fraction of the data set. Okay, that's the intuition for the algorithm. The next slide, I think, is a pseudocode, and after that it's a proof, which I might skip. So if there are any questions at the conceptual level, please ask me now. Yes?
In order to analyze the running time of the algorithm, I guess you need to argue that it removes at least 1 point in
Yes, yes. So it does. Okay, and this is essentially, if you see, I mean, let me show you the pseudocode, okay? So that's the pseudocode. Suppose we reach in step 4, and we can find the T such that this is the case. So this implies, because the right-hand side is positive, that you remove at least 1 point, okay? So you have a discrete set of points. You know, if this is positive, you remove at least 1 point in every iteration, okay? You can do better than that. In fact, if you analyze this correctly, the number of iterations of the algorithm is going to be something like O tilde of D, where D is the dimension, while the obvious upper bound would be O tilde of, or O of number of bad points. The number of bad points is epsilon times n, which is basically d over epsilon in this case. So we gain a 1 over epsilon factor. So you can analyze the number of iterations more carefully. So overall, the running time of this algorithm is going to be nd squared. Okay. All right, so let me read this pseudocode. So the input is an epsilon corrupted set of points in the strong contamination model, and the output is a subset of the point that's less corrupted, or an estimate of the mean that works. And the algorithm is estimate the empirical mean and calculate the empirical mean and the empirical covariance. If the spectral norm of the empirical covariance is small, smaller than the guarantee we need from the key lemma, then output the empirical mean. Otherwise, project the data in a direction of large variance, larger than this quantity, and then find the threshold such that the fraction of the points that are far from the median in this direction is larger than what it should be, and remove all the points of the set that are basically above the threshold, or retain the rest. That's the algorithm. So there is one point that I haven't shown, which is a little bit technical. In particular, step 4 here says find T such that, and it is possible that such a T doesn't exist, right? In which case, what are we doing here? So the only way that this is going to give you something useful is if this threshold actually exists. You can actually remove some points. And the intuition for that is that why this is the case is that, again, if this thing was violated, if there was no T, such that this condition holds, then the variance in the direction of V star wouldn't be as large as we assumed it to be. Wouldn't be at least 1 plus epsilon log 1 over epsilon. I have 15 minutes. I'm not going to actually show you this proof, but it is basically a calculation similar to the one that we did before. We just need to show that, what I said intuitively holds, it's just an integral. I'm not going to do it, but you can look at the slides when they are available. And I think that completes the analysis of this algorithm. So in the rest, maybe in the remaining 15, 14 minutes, I'm going to give you an overview of stuff that has been done since then. So are there any questions about this algorithm? Okay, so let me move forwards. So summary, for robust mean estimation, we developed and exploited a certificate of robustness. It turns out that this certificate is the spectral norm of the empirical covariance being close to its expected value. The way we exploited this certificate for the filtering algorithm was to check if it's satisfied in the entire space. And if it's not, if it's violated, then we found a subspace. This subspace happened to be a direction for the algorithm I described, where the behavior of the outliers is significantly different than the behavior of the inliers. So what we actually used here is a concentration property of the data, but not on the global scale, but on the scale of specific directions or specific subspaces. So we use more information than just what the naive pruning actually does, okay? Which basically tells you that the data is going to be concentrated within root D in D dimensions. Then we used that subspace to detect and remove outliers. So no one tells you that this subspace needs to be a line. It can be a linear subspace of larger dimension, it can be a plane or higher dimension subspace. It doesn't need even to be linear. You can project, you can look at values of low degree polynomials on the data. And in fact, this is something that has been used in subsequent applications of this framework for robustly estimating higher moments. I guess that's it for the summary. Now, one thing that I will not have time to mention is that there is a soft outlier removal version of this filter algorithm. So what this algorithm does is that it iteratively finds directions where the variance is larger than what it should be, and it uses the projections to remove points and say, okay, these points are outliers, I have fixed this direction, I'm going to do it again. Another thing you can do is actually put weights on the points, okay, like real weights, let's say between 0 and like 1 over n, and try to to assign these weights in such a way so the weighted empirical covariance is going to be close to the identity, okay? So basically this says that, okay, there is a convex set, find weights such that the weighted empirical covariance after you reweight the points is going to be close to the identity. So this is like almost an SDP. If we're able to find a point in this set, which is a convex set, then essentially our key lemma says that the empirical mean weighted appropriately by these weights would work. This is a sort of straightforward generalization of what we have said so far. One of the issues is that this is a convex set, but it's an unknown convex set because it's defined with respect to the unknown nu that we are looking for. But there is a way to develop a separation oracle for it, which I'm not going to show you too much. The reason that I'm mentioning this, the separation oracle is this, I don't need to parse it, but basically what it says is that if I find the direction of large variance, I do not remove data, I just reweight the data. So I impose some kind of linear inequality on the data, which imposes a constraint on the weights, and this is how I sort of continue. So at the end of the day, I would use that with ellipsoid. Now, why do we care about separation oracles in this setting? And well, this framework is actually pretty clean and it generalizes quite well. I think some of the subsequent work that used the sum of squares methods for generalizations of this problem starts from a convex program of this form. So I think it's useful to know. Now let's go to extensions. Someone asked during the first part, do we need to know that the covariance is identity, and are these things necessary? The answer is no. In fact, even in the first paper, I think in the Lai, Rauv, and Pala paper, immediately there is an implication that if you have some kind of bounded moment conditions, you can estimate the mean. So let me show you what is the, I guess, first of all, what we've shown so far is not for the Gaussian distribution, okay? The only thing that you need is that you know the covariance of the data before the corruptions took place, and you know that you have sub-Gaussian concentration. So the exact same algorithm works with the exact same guarantee if you have sub-Gaussian distributions. So this is point number one. This is in the strong contamination model. So this still doesn't give O of epsilon, okay? So, but the answer is that it's not possible. So if the only assumption that you have about your data is that sub-Gaussian, epsilon root log over epsilon is information theoretically optimal. Do you see why? Because if you have a sub-Gaussian distribution in one dimension, and you remove an epsilon tail, it remains sub-Gaussian. So there is no way to know if the true distribution is the one with the tail or without. So this epsilon root log is really, what the algorithm was optimized for. It was working for sub-Gaussian distributions. And for that setting, it cannot be improved. But of course, for Gaussians, one would hope that we can do better, right? So I argued that O of epsilon is possible, information theoretically. So can we do that? Gaussian is a pretty basic case. So ideally, we would like to get the information theoretically optimal error in polynomial time. So the reason that this is in parentheses is because it was open at that time. So there's an answer, a positive and a negative answer to this question. So the positive answer is from a follow-up paper with the same set of authors that in the additive model, you can get O of epsilon. So there is a polynomial time algorithm that robustly learns a mean of a Gaussian with no covariance within a constant times epsilon error. Okay, in fact, we even know the constant. And this doesn't only work for the Gaussian, it works as long as you know that for every projection, every one-dimensional projection, the median is a good estimator of the mean. But it's like much less general than what I have described so far. So in the additive model, we can do it. Can we do it in the strong model? And for that answer, we don't know, but we have some evidence that we cannot. Okay? In particular, there is this model, which is called statistical query model. And in this model, at least, we can show, so this is with Daniel Ken and Alistair Stewart, my postdoc, that any improvements on the error guarantee of the filtering algorithm requires super polynomial time. Okay, so this is, it suggests that maybe you cannot do better than that on Gaussians. So do people know what the SQ model is?
Can we just go back and there was an information theoretic bound which said O of epsilon is achievable, right? In this case, or was it?
Yes. So this is exactly. So this is a setting where there is a difference between the information theoretic and the computational, assuming that this model is complete. Okay, yeah. That's the point. The point is that in the beginning I said, can we achieve the best of both worlds? It seems that for the Gaussian, even this is not the case. At least if you care for really polynomial time algorithms. Now let me say a few words about the SQ model. I don't have much time. So it's a restricted model of computation. The point is that instead of actually directly accessing samples, you can adaptively query expectations of functions of your distribution. The message here is that many algorithms that we have, or almost all algorithms that we have in this setting, are askew. And in particular for these problems that I'm discussing in this work, there's nothing that's not askew. So if we want to improve that, then we would need to do something else. It's not impossible, but I won't work on it. So this is slide number one. Slide number two is that there has been a lot of work of analyzing the complexity of these types of algorithms. There is a general methodology of proving lower bounds. And roughly speaking, what it suffices to do is find a set of distributions in your family that are nearly uncorrelated under some kind of appropriate inner product. So essentially the problem of proving computational lower bounds in this model roughly amounts to producing an explicit construction. So the question is how to do that. Let me tell you how we do that for this problem. It works more generally. So we construct our hard distances as follows. We pick some direction, and the projection of our distribution in that direction is going to match the first few moments of a standard Gaussian. Okay, so let me show that. So there is some direction, and we project the distribution in this direction. So it's going to be some one-dimensional distribution A. This can be anything, as long as it matches the first m moments of a standard Gaussian. And the orthogonal complements, the distribution is going to be standard Gaussian. And now the theorem says that we cannot find this direction unless we either use many queries to our oracle, or every query has very high accuracy. So the minimum of these two quantities is basically a lower bound on the running time. So this gives basically a lower bound of d to the m. Okay, so where m is the number of matching moments. And now how do we use that construction to prove the lower bound I just mentioned? Well, we make this one-dimensional distribution A to be a corrupted one-dimensional Gaussian whose mean is epsilon root log over epsilon far from the true mean, and that matches many moments with that. So this is an approximation theory type of guarantee you can show. And by plugging it in, you get these lower bounds. And like intuitively, the reason that the problem is hard, because you cannot use low degree moments. Since you match moments in this one direction, you match all the tensor moments after degree d, so you have to look at moments of degree n+1. And also you cannot use random projection. So this is a point that I was discussing with Ravi. So probably, if you use a random projection for this type of construction, you would need to look at exponentially many random projections until you hit anything interesting. This is a lemma. A lemma that says that if you look at the distance of a random projection from standard Gaussian, it's going to be exponentially close. And okay, there are some interesting analytic tools that we use to prove that. So there is some interest for the complexity theories of this group. So can we actually prove hardness for this family of instances under different assumptions? The technique applies to many other problems. Okay, so this is robust mean estimation is one of those problems, but essentially for many other types of robust and non-robust problems, this type of technique gives you essentially tight computational lower bounds. You don't need to parse this table. How could you? Finally, for the mean, what happens if we don't know the covariance? Okay, if we don't know anything. Let's say that we only know the covariance is somehow bounded. Let's say bounded in loaner ordering. Then the answer is basically root epsilon. This is the information theoretically optimal answer, and a variant of the filtering algorithm works. So now I'm going to give you samples from a distribution. I don't know the covariance matrix. The only thing that I know that it's bounded like this. And I can find an estimate of the mean, which is accurate within error root epsilon, where epsilon is a fraction of corruption. So this is easily seen to be the information theoretically optimal error, and we can achieve it under those assumptions, and we can achieve it in polynomial time. Finally, there are similar qualitative results for the covariance, which I'm going to completely skip. There's going to be a talk, a fellow's talk by Jerry Lee after this talk. You can ask him if you want. So let me summarize. So what did I give today? I gave you a few techniques that yield computationally efficient and robust estimators for some basic high-dimensional problems. These are the first algorithms of their kinds. And we described essentially 2 or 3, depends how you count, different methodologies to do this. There has been a lot of work in this area since these papers appeared. In particular, there have been results on more general models like graphical models. I guess I showed you some of these computational statistical trade-offs. Perhaps, unrelated, perhaps like not directly, not immediately, obviously related applications for clustering in mixture models, and also in supervised learning. There are these old models of Valiant from the 80s on malicious pack learning. Now we have algorithms that can actually learn in this model low-degree polynomial threshold functions and polytopes with a bounded number of facets. In more ML-ish related problems, we have algorithms for robust linear regression and more generally for robust stochastic optimization. So there has been a lot of work. So this is a number of subsequent related works on various models. So this is certainly doesn't cover everything that has happened since then. Jerry is going to tell you about how to use the sum of squares hierarchy to robustly estimate the mean under some kind of restricted version of sub-Gaussian assumption where the covariance is unknown. Now, okay, in terms of open questions, I guess usually I like to give this open question. It's a little bit too generic, like find a problem that we know how to solve efficiently in high dimensions without the corruptions and make the algorithm robust. But let me give one concrete open problem, which is still open. It's not going to be open in 6 months, but it's open now. So even for two arbitrary Gaussians with arbitrary mean and covariance matrices, so not necessarily spherical, we currently do not have an algorithm that gives you a robust estimation in terms of total variation distance. Okay, so a strong error metric. The Gaussians could look something like that. So this is a sort of a problem at the frontier of current research. And more generally, the future goal is to develop a general algorithmic theory of robustness. So we want less ad hoc algorithms. So I give you a problem, a robust estimation problem, give me an optimization problem corresponding to that, somehow automatically, that I can solve efficiently and it's going to give me a solution that's robust. So that's the idea. And there are many challenges that I'm interested in. If you're interested in any of them, come talk to me later. And in terms of workshops, I try to compress like 8 hours of tutorials to 2 hours. So there was a workshop last week, or 2 weeks ago, that we co-organized with Daniel Kane. The slides are online. And a workshop that's actually much broader than what I talked about in beginning of November with these highly esteemed co-organizers. And at this point, I think I'm going to conclude.
Questions? For somewhat heavy-tailed data, is there any hope of getting something?
How heavy-tailed? Like more than bounded second moments?
Let's say it has a second moment.
I mean, if you have a bounded covariance, you can get that, right? You can get the sigma root epsilon. If you don't have a bounded covariance, generically,
How good, I mean, you don't very, yeah.
let me go back. So the question that David asked, what happens when you have heavy-tailed data? So one type of heavy-tail assumption is that the covariance matrix is, or that Chebyshev's inequality is tight. Okay, let's say, if you have that, then this is the guarantee you can get. And if this is the only assumption that you have, this is the best guarantee that you can get information theoretically. I mean, this doesn't cover everything because there are some extreme cases that do not uniformly satisfy that, and we can still do. But yeah, there is still work on that. Another thing I should say is that for heavy-tail data, there are like other notions of robustness that people have looked at that do not fall into this category. In particular, like Gabor has median of means estimator, and various estimators like have good properties, but they're like technically sort of unrelated to what I talked about. Yes.
So this work you described has like it's very strongly using that you're trying to estimate a Gaussian, right?
Okay, I tried to make this point that it doesn't. That was the presentation.
Right. So in the main part of the presentation, and then you mentioned afterwards that there's been extensions to all these other techniques. The general question I have is like, does every new problem need, like, it's very specific about what the model space is you're looking at, and it's.
Okay, so so the answer is that okay, even the original papers, they had sort of much more general results, so results under much more general assumptions, why I did not even state here. But I mean that's the goal. Okay, so but roughly speaking, now we know that you make the concentration better in some sense, or you get a better control of the higher moments, you get better guarantees. That's something that we more or less know how to do, but we're not there yet.
Other questions? Let's think of